Engineers utilize Dassault Systèmes CATIA software to model complex aerodynamic surfaces, creating a digital twin that ensures every component fits perfectly before the physical manufacturing process begins. Supercomputers run computational fluid dynamics, simulations, analyzing airflow over virtual airframes to optimize lift-to-drag ratios and minimize radar cross-section signatures without requiring expensive wind tunnel testing. Raw titanium ingots are melted in vacuum arc furnaces, purifying the alloy to aerospace-grade standards required to withstand the immense structural loads of supersonic combat maneuvers. Massive hydraulic presses stamp heated titanium billets into rough structural shapes, aligning the metal's grain structure to maximize strength-to-weight ratios for critical load-bearing aircraft bulkheads. 5-axis CNC milling machines carve complex geometries from solid forged blocks, removing up to 90% of material to create lightweight, single-piece structural frames for assembly. Ultrasonic probes scan the machined titanium parts, searching for microscopic subsurface voids or inclusions that could initiate catastrophic fatigue failure during high-stress flight operations later. Automated cutting machines slice rolls of carbon fiber pre-preg tape into precise ply shapes, utilizing nesting algorithms to maximize material yield and minimize expensive composite waste. Laser projectors outline precise ply placement on the mold tool, guiding technicians to lay down carbon fiber sheets with distinct fiber orientations for specific structural loads. Robotic tape laying machines apply carbon fiber plies to complex contoured surfaces, ensuring consistent compaction and eliminating human error in the creation of large fuselage skins. Technicians seal the composite layup under vacuum bags, extracting air to apply atmospheric pressure that consolidates the layers and prevents voids during the thermal curing process. Huge autoclaves subject the bagged parts to high heat and pressure, chemically cross-linking the resin matrix to transform soft fabric into rigid, high-strength aerospace structural components. Water-jet systems transmit ultrasonic waves through cured composite skins, generating C-scan maps that verify the laminate is free of delaminations or porosity prior to assembly usage. High-pressure water-jet cutters trim the cured composite parts to final net shape, preventing heat damage to the resin edges while achieving tight dimensional tolerances for fit. The forward fuselage assembly begins with the aluminum cockpit tub, the rigid pressure vessel designed to protect the pilot and support the ejection seat rails securely. Mechanics rivet aluminum bulkheads to the cockpit floor, creating the skeletal framework that defines the nose geometry and supports the mounting of sensitive avionics radar equipment. Automated drilling units crawl over the forward fuselage jig, boring thousands of precise holes through aluminum lithium skins to prepare the structure for permanent fastener installation steps. Technicians install flush head rivets along the fuselage skin, ensuring the exterior surface remains aerodynamically smooth to minimize drag and maintain the aircraft's low observable stealth characteristics. The machined titanium canopy sill is bolted to the cockpit longerons, providing a high-strength interface for the transparency that must withstand pressurization cycles and bird strikes. Assembly of the mid-fuselage starts with the serpentine air inlet ducts, shaped to shield the engine face from radar waves while delivering clean airflow to compressors. Carbon fiber intake ducts are integrated into the fuselage structure, wrapped in conductive coatings to dissipate electromagnetic energy and prevent radar reflections within the engine tunnel. Technicians assemble the internal weapons bays, installing heavy-duty door mechanisms and hydraulic launchers capable of deploying munitions rapidly while maintaining the aircraft's stealth profile during combat. The forward and mid-fuselage sections are aligned using laser trackers, ensuring the digital datum planes match perfectly before the sections are permanently joined into one structure. Mechanics bolt the massive main wing, carry-through bulkheads together, uniting the fuselage sections with the primary structural spine that supports the wings and main landing gear. Wiring harnesses are manufactured on long form boards, where cables are cut, labeled, and bundled into complex looms that will route power and data throughout the airframe. Electricians route the main wiring looms through the fuselage, securing them with cushioned clamps to prevent chafing and ensure signal integrity in the high-vibration flight environment. Titanium hydraulic tubes are bent to precise geometries using CNC benders, then chemically cleaned to remove contaminants before installation into the fuselage's confined system bays. Thermal acoustic insulation blankets are wrapped around the cockpit and avionics bays, protecting sensitive electronics and the pilot from the extreme cold and noise of flight. The forward pressure bulkhead is reinforced to support the AESA radar array, ensuring the sensor remains rigid and boresight aligned during high-G combat maneuvering sequences. The dielectric radome is manufactured from specialized quartz materials, tuned to be transparent to on-ship radar frequencies while protecting the antenna from aerodynamic heating and rain. The nose landing gear strut is installed into the wheel well, featuring a dual-chamber oleo design to absorb catapult launch loads and arrestment impact forces reliably. Heavy-duty main landing gear trunnions are secured to the airframe, designed to support the aircraft's full landing weight and absorb the kinetic energy of touchdown events. Technicians install flexible bladder tanks into the fuselage cavities, connecting interconnects and vent lines to create a sealed fuel volume that maximizes range and survivability. Heat shields made of titanium and ceramic tiles are installed in the engine bays to protect the composite airframe structure from the extreme thermal radiation emitted. The auxiliary power unit is mounted in the fuselage, a small gas turbine that provides electrical power and bleed air for main engine starting and operations. Composite access panels are fitted to the fuselage, checked for flushness and gap tolerances to ensure they do not compromise the aircraft's radar cross-section requirements. The assembled fuselage is moved to a paint booth where a corrosion-inhibiting epoxy primer is applied, sealing the metal and composite surfaces against environmental degradation risks. Technicians apply conductive sealant to all fuselage panel seams, ensuring electrical continuity across the airframe skin to manage lightning strikes and electromagnetic interference effectively. A ground hydraulic mule pressurizes the aircraft systems, allowing mechanics to leak-check the newly installed tubing and verify the operation of landing gear and bay doors. Power is applied to the main buses to continuity check the wiring harnesses, ensuring no short circuits exist before sensitive avionics computers are connected to the grid. The completed fuselage assembly is lifted by overhead cranes and placed on a transport dolly, ready to move to the wing mating station for the next phase. Heavy machining centers craft the titanium wing spars, the primary load-bearing members designed to support the aerodynamic lifting forces and fuel weight during flight operations. Assembly mechanics attach precision-machined aluminum ribs to the spars, forming the skeletal ladder structure that defines the airfoil shape and provides rigidity to the wing. The lower carbon fiber wing skin is positioned onto the fixture, serving as the foundation for the wing box that will eventually contain the fuel supply. Automated drilling gantries pass over the wing structure, creating thousands of fastener holes through the thick composite skin and titanium substructure with high-tolerance precision. Robotic end effectors insert and torque titanium fasteners into the wing skin, securing the assembly to withstand the immense bending moments experienced during high-G combat turns. Technicians apply polysulfide sealant to the interior of the wing box, transforming the structural cavity into a leak-proof wet wing capable of storing jet fuel. The leading edge flaps are assembled with rotary actuators, providing the variable camber required to increase lift during takeoff and maintain maneuverability at slow speeds. Trailing edge flaperons are attached to the wing structure, combining the functions of flaps and ailerons to provide roll control and lift augmentation during flight. Mechanics install the wingtip missile rails, integrating the wiring interfaces that allow the pilot to communicate with and launch heat-seeking air-to-air weaponry in combat. Navigation lights and formation strip lighting are embedded into the wing edges, ensuring visual visibility for night operations while maintaining the flush aerodynamic outer mold line. The vertical stabilizer structure is assembled from composite skins, bonded to a honeycomb core, providing a lightweight yet stiff surface for directional stability and yaw control. Hydraulic rudder actuators are installed within the vertical tail, connecting to the flight control surfaces that will manage yaw and coordinate turns during complex maneuvers. The horizontal stabilizers are manufactured as single-piece composite structures, designed to pivot entirely to provide powerful pitch control and supersonic trim for the fighter aircraft. Heavy-duty pivot shafts are inserted into the horizontal stabilizers, the critical interface point that transfers the massive aerodynamic loads from the tail to the fuselage. Technicians bond the final composite skins to the empennage structures, placing them in an oven to cure the resin and achieve maximum structural strength properties. Precision machining centers mill the root attachment points of the vertical and horizontal tails, ensuring perfect alignment when mated to the main fuselage assembly fixtures. The fuselage is positioned in the mating cell, supported by laser-guided jacks that level the airframe to within thousandths of an inch for wing integration. An overhead crane slowly lowers the completed wing module, requiring careful coordination to align the carry-through bulkheads without damaging the composite skins or interface surfaces. Laser trackers verify the wing sweep angle and dihedral, ensuring the aerodynamic geometry matches the design specifications perfectly before the permanent attachment process begins. Mechanics install large-diameter tension bolts to secure the wing to the fuselage, torquing them to specific values to ensure structural continuity across the airframe. The vertical stabilizers are hoisted into position on the aft fuselage, aligned with the mounting lugs to ensure the twin tails are perfectly parallel and vertical. Technicians slide the horizontal stabilizer shafts into the fuselage bearings, connecting the surfaces to the actuator packages that drive their movement during flight control inputs. Aerodynamic fairings are installed over the wing and tail roots, smoothing the airflow at the junction points to reduce drag and prevent turbulent interference flow. Flight control pushrods are connected between the actuators and surfaces, establishing the mechanical link that translates hydraulic power into aerodynamic movement for the pilot. Hydraulic lines are connected from the fuselage to the wing systems, powering the leading edge devices, flaperons, and landing gear retraction mechanisms for operation. Electricians mate the wing, wiring harnesses to the fuselage main power bus, enabling the distribution of electricity to wingtip sensors, lights, and weapon stations. Fuel transfer lines are coupled between the wing tanks and the fuselage management system, allowing the flight computer to balance fuel loads for center of gravity control. The main landing gear struts are installed into the wing trunnions, completing the support structure that allows the aircraft to operate safely from paved runways. Retraction actuators are connected to the landing gear, providing the muscle to stow the wheels inside the fuselage to reduce drag for high-speed flight. Gear doors are rigged to close flush with the fuselage skin, a critical step to maintain the low observable stealth signature when the wheels are retracted. A hydraulic rig cycles the landing gear, verifying the retraction sequence and ensuring the uplocks engage securely to hold the gear during high-G maneuvers. Carbon brake stacks are installed on the axles, providing the immense stopping power required to halt the aircraft safely during maximum weight aborted takeoff scenarios. High-performance tires are mounted to the wheels, rated for the extreme speeds and loads encountered during takeoff rolls and landings on rough airfield surfaces. The aircraft is lowered onto its wheels for the first time, transitioning from the assembly jigs to its own suspension system for the remaining build. Tow bars are attached, and the aircraft is moved to the final assembly line, where systems integration and mission equipment installation will be completed. Ground power is connected to energize the electrical bus, allowing technicians to perform the first smoke test to ensure no wiring faults exist in the system. The avionics bays are prepped with cooling racks, ready to receive the mission computers that will process radar, navigation, and communication data for the pilot. Radar absorption material is applied to the landing gear struts, reducing the radar reflection from these complex metal shapes when the gear is temporarily extended. The cockpit is finalized with the installation of the main instrument panel brackets, preparing the workspace for the pilot's displays and control interface inputs. The airframe moves into the vertical docking station, a specialized rig that surrounds the aircraft to provide access for the final dense systems integration phase. Vertical docking stations allow simultaneous access to all internal compartments, facilitating the rapid, parallel installation of critical subsystems while strictly maintaining structural alignment within the controlled environment. Technicians route thousands of labeled wires through cushioned clamps, creating the aircraft's nervous system while ensuring signal integrity and protection against vibration during high-G flight maneuvers. Mechanics install titanium hydraulic lines using automated swaging tools, creating permanent, leak-proof seals designed to withstand 4,000 pounds per square inches, pressures essential for powering heavy flight control surfaces. Integration of high-capacity heat exchangers manages the immense thermal loads generated by avionics, ensuring critical electronic components remain within operational temperature limits during sustained combat operations. The installation of glass, multifunction displays, and the side-stick controller establishes the primary human-machine interface, designed to maximize pilot situational awareness while minimizing physical workload during combat. Liquid-cooled supercomputer modules are slotted into avionics racks, serving as the sensor fusion brain that processes disparate data streams into a unified tactical picture for the pilot. A crane positions the active electronically scanned array antenna, a fixed plate system requiring precise bulkhead alignment to ensure beam agility and extended detection ranges without mechanical movement. Mechanics connect hydraulic actuators to control surfaces, verifying null positions with digital inclinometers to ensure precise aerodynamic response and flight safety integrity during high-speed maneuvering sequences. Rapid population of structural bays with avionics and hydraulic components transforms the empty airframe shell into a dense, functional machine, optimizing internal volume for maximum system capability. Inside wing tanks, technicians install transfer pumps and sensors within a hazardous confined space, ensuring reliable fuel delivery and center of gravity management across all flight regimes. Installation of molecular sieve canisters eliminates the need for liquid oxygen bottles, generating breathable air on demand to support extended mission durations and reduce logistical support footprints. The polycarbonate transparency is mated to the aluminum frame using conductive sealant, ensuring electrical continuity across the surface to prevent radar reflections from compromising the aircraft's stealth signature. The 6-barreled rotary cannon is integrated into the wing root, connecting the linear linkless feed system to provide reliable, high-volume firepower for close-range air superiority engagements. Technicians adjust linkage rods to verify landing gear, door compression, ensuring a flush, aerodynamic seal that minimizes drag and maintains low observability during cruise flight configurations. External power activation energizes the avionics suite for the first time, allowing ground crews to verify telemetry streams and system health before proceeding to engine installation. Technicians prepare the massive turbofan engines by removing protective covers, inspecting external plumbing and accessories to ensure the power plants are ready for immediate airframe integration. Rail-guided lift carts slide the engines into the rear fuselage tunnels with millimeter precision, a critical operation requiring coordination to avoid damaging internal structures during heavy installation. Mechanics engage locking pins to secure the engine to airframe rails and connect digital control harnesses, establishing the vital link between the pilot and the propulsion system. Ceramic matrix composite pedals are installed on the exhaust nozzle, interlocking to withstand extreme heat while providing the thrust vectoring capability essential for superior maneuverability. With engines installed and lower access doors bolted shut, the aft fuselage achieves structural closure, sealing the propulsion bays to maintain aerodynamic continuity and stealth integrity. The assembled aircraft enters a climate-controlled robotic paint facility, where sterile ventilation and humidity controls prepare the surface for the application of advanced radar-absorbent coatings. Technicians apply precision masking using laser-projected templates, protecting sensors and transparencies to ensure coating boundaries align perfectly with the aircraft's calculated radar cross-section design requirements. Robotic arms dispense conductive putty into fastener depressions and seams, creating a perfectly smooth surface topology that eliminates radar scattering features before the primary coatings are applied. A metallic silver base coat is robotically applied to provide electrical conductivity across the skin, a fundamental layer for managing surface currents and dissipating electromagnetic energy. Robots apply radar-absorbent material in calculated layers, utilizing precise spray paths to ensure uniform thickness that effectively traps and dissipates incoming radar waves as heat. Specialized technicians hand-paint complex sawtooth edges on access panels, ensuring these critical discontinuities scatter radar waves effectively without compromising the overall low observable signature of the airframe. The entire booth becomes a curing oven, using infrared heaters to thermally set the complex chemical structure of the stealth coatings, ensuring durability and performance stability. Inspectors utilize robotic probes and terahertz scanners to map coating thickness at thousands of points, verifying compliance with strict metrology standards required for operational stealth certification. Robotic arms scan the airframe with radar emitters, simulating threat frequencies to verify that the applied coatings successfully absorb energy and meet the classified signature specifications. Technicians spray low-visibility markings that blend with the fuselage, applying essential military identification while maintaining the visual camouflage and low-contrast requirements of the stealth design. The installation of the ejection seat connects the pilot to explosive canopy jettison lines, finalizing the escape system that ensures aircrew survival during catastrophic flight failures. Lowering the completed canopy onto the cockpit seals the pressure vessel, mating the gold-tinted transparency with the fuselage to complete the aircraft's external aerodynamic profile. Hydraulic systems drive all control surfaces through their full range of motion, verifying the flight computer's ability to command rapid, coordinated adjustments for stable flight. The single-point refueling port is connected to fill the aircraft with JP-8, allowing engineers to calibrate fuel quantity sensors and check the integral tank system for leaks. The aircraft rolls onto digital scales to verify the center of gravity falls within strict engineering limits, a critical check to ensure stable flight characteristics before delivery. Hangar doors open to reveal the completed aircraft, marking the transition from manufacturing assembly to flight line operations as the stealth fighter enters the natural environment. Secured to the tarmac, the aircraft runs engines at full afterburner, demonstrating raw propulsion power and verifying the structural integrity of the exhaust system under thermal load. The pilot navigates the taxiway under the aircraft's own power, testing braking systems, and nose-wheel steering to validate ground handling characteristics before attempting the first flight. The fighter accelerates rapidly and climbs vertically on full afterburner, visually demonstrating the thrust-to-weight ratio and aerodynamic performance capabilities that define its air superiority dominance. The manufacturing lead transfers the signed documents to the delivery pilot, formally concluding the production cycle and releasing the fully operational weapon system to the squadron.
Clear on the left side, tail moving past the hangar line.
Confirm, steady as she goes.
Rudder and elevators checked. Flaps configured for departure. Final review complete. Positioning runway 18 right.
Rollout complete, steering engaged. Copy that, bring her to a stop right here.
Did you log the hydraulic levels?
The fine nipples?
Yes, showing green across the board.
I'm showing a slight temperature variation near the access panel.
Let me check that with the probe.
Engine cover secure.
Roger, Patat, caps complete. Final walk around initiated.
Canopy is green and secure. Final inspection complete.
Roger that. Entering cockpit.
Tower, Tug 1 proceeding to the arming area, runway 27.
Roger that. Tug 1, maintain current vector.
The cycle of operations continues.